Introduce Gordon Baym, renowned physicist, one of the most diverse physicists in the country. Gordon was born in Brooklyn.
No, I was born in Manhattan.
You were?
Yeah.
Okay, you grew up in Brooklyn, about 3 blocks away from me, born 10 years before me. Went to the same public school that I did.
241.
Before I did, 10 years before I did. I didn't know that until 60 years later. Let's see. After graduating from PS 241, Gordon went to Brooklyn Tech.
That was complete. I grew together.
Went to Brooklyn Tech, got his BS at Cornell, and his PhD at Harvard with Julian Schwinger. He started at University of Illinois in 1963 as assistant professor, and he's been there ever since. He's presently emeritus professor both in engineering and in physics at Champaign, Urbana. Made seminal contributions to matter under extreme conditions, from atomic physics, from Bose-Einstein condensates to neutron stars, crusts and interiors. He's written 3 books. This is what I learned quantum field theory and statistical mechanics from Kadanoff and Baym. He also wrote lectures on quantum mechanics, which was a graduate text, and Landau theory and liquid theory with Chris Panic. He's won many prizes: Hans Bethe Prize, Lansager Prize, Feinberg Memorial Prize, and this year he won the highest award that the American Physical Society gives, which is the APS Medal for Exceptional Achievement in Research. Okay. He's also, I know Gordon for the past 2 decades about. We're both on the board at Reports on Progress in Physics, which is a British journal. He's now chairman of the board. And you were chairman of the board till this year. Okay. And what we do there is the board members or different specialties, we all come every year to a meeting in London and present what's the most exciting stuff that's happened in their field during the year. Okay, Gordon always gives the best talks, and at the end of everybody's talk, Gordon always explains to the rest of us what the other talks were about and answers all the questions. Okay. He's going to tell us today about neutron stars, of which he's an expert. He'll tell us what's hot and new in neutron stars. Gordon, what?
Continue, you're doing well.
Let's see what I can do. Okay. Maybe I should get you to sign this.
Right.
The meeting is being recorded.
Yeah.
The conference is being recorded.
So anyhow, here's a neutron star centered over NYU, and it goes as far as the Bronx in one direction. It encompasses our old neighborhood in Brooklyn over here. And it goes as far as the north in the other direction. So typically around 12 kilometers in radius. Still
not going
advance the
forward?
slides. Okay, I have to use the mouse here. Okay. So this is a Feynman diagram of a neutron star. Typical radius. They range in masses from about solar mass up to slightly over the mass, twice the mass of the sun. Those are observed neutron stars. Radii are in the range of 12, 13 kilometers. And are being learned much better very recently. Typical temperatures are 10 to the 6, 10 to 9 Kelvin, or this is KeV to some MeV range over the life of the star. So that they start out at temperature around MeV and cool down to surface temperature of around 10 to the KeV. The baryon number is about 10 to 57, which is the same number as baryons as you find in the sun. This number is actually a very nice number. Does anybody know the relation of this number to the fine structure constant for gravity? It's a gravitational fine structure. Okay. define of the gravity, mass of the protons through Newton's gravitation constant. C alpha G minus 2/3 power. It's not an accident. It's real physics. This sets the scale of everything. And so what, and the big magnetic fields, which can range from something 10 to 6 Gauss up to even as high as 10 to 16 Gauss, very high. So the structure is pretty spherical. One could have mountains that are perhaps at most 1 millimeter high. Does anybody recognize the mountain?
Probably yes. but no.
It's so percent. Reduced in size. One has an outer layer of ordinary metal, nuclide electrons. Then there's a region where one gets to see a free neutrons permeating nuclei as well. I'll describe this in more detail. And there's plenty of region called posited nuclei. That's the outer crust. Then at a density of around 210 to the 14 grams per square centimeter, per cubic centimeter, the system degenerates into a liquid of neutrons, protons, and electrons, nuclear matter. And as one goes further in, the question is what happens in the deep interior. And there's possibly a continuous transition to a quark-hadron plasma. I want to focus on much of this over the course of this talk. But the first few words of history. Because there's been a lot of confusion in the literature, which I'm sort of responsible for. The neutron was discovered in February 32 by Chadwick. He sent this lovely letter to Bohr announcing the discovery of the neutron. But Chadwick didn't really believe what he had to say. Even though he got a Nobel Prize, he wrote here, this is February 32, this is February 29th, just a few days later. He says, Dr. Chadwick only smiled, however, when asked if his discovery had practical importance. I'm afraid neutrons will not be of any use to anyone. But here's a guy who discovered a new elementary particle. But you now know it's not elementary, would be, of course. But he didn't like that. He wrote, this is now September. He can't stop. The belief that the neutron is a new ultimate particle like an electron or proton was challenged today by Dr. Chadwick. Young Cambridge scientists discovered the elusive neutron last winter. He just didn't believe that there could be a particle called neutron and a particle called a proton whose masses were so close to each other. It just had to be a composite of a proton and an electron. They're very, very
I
simple.
forgot to mention, he also does work on history of physics.
Oh, thank you. So anyhow, the first serious proposal of neutron stars was actually Bada and Zwicky. This is Bada, Walter Bada, for Zwicky here, characteristic photo of him. And they had this remarkable paper in the Bulletin of the American Physical Society in December 33, where they posited the idea that in a supernova, the central core will collapse down into a neutron star. Zwicky actually did an estimate of the size of a neutron star. And so it got this 12 to 13 kilometer number on the basis of nothing. He was absolutely remarkable man. His other big contribution. Does anybody know what his other big contribution is?
You mean it's Vicky?
Huh?
Zwicky?
Vicky.
But dark matter.
Dark matter.
Even get
Dark matter.
the
Don't go material. Yeah. Well, nothing much happened. In the late 30s, Oppenheimer and Volkov calculated a simple model of neutron stars made of free neutrons. Of course, at this point, the appropriate general relativity was developed by Tolman, and Volkov. And they get a total mass of 0.7 solar masses. That's the maximum mass they could have. But now, because we know they're much heavier than neutron stars, what does that tell you? It tells you right away, interactions must be very important. Nothing very much happened. People were playing games with it for a long period. And finally, John Wheeler wrote in 66, a cool superdense star is fainter than the 19th magnitude, and therefore hardly likely to be seen. The rapidity of cooling makes detection even more difficult. And remarkably, next year, those stars were detected, which we know now are neutron stars. So here's Jocelyn Bell. And here's a transcripts actually seeing two separate stars, bloop, 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 bloop. The bottom, these are 1 second intervals here. And so these are two separate stars over here. She called them LGM for little green men. There's a very nice quote I'll get to in a second. So her thesis advisor was Tony Hewish. And Hewish, he actually died last Monday. And it's over in the New York Times, it just appeared. And this is the most damning, the single most damning obituary ever written. I mean, half the obituary is yelling at Hewish for for getting Nobel Prize instead of Jocelyn Bell. Quite amazing. Anyhow, but late in the spring of '68, both Franco Pacini, Tommy Gold identified pulsars as rotating neutron stars, and so at this point, neutron stars were discovered. First time.
Identified in the sense of theoretically. I mean, they
Yes, they
made
couldn't
the
be
argument,
white, they
they
had to
made
be
the case that
compact.
that's what they would be.
They had to be high density objects, a lot of energy.
They didn't
and
demonstrate.
they could not be white dwarfs. And they were unrotating. So anyway, here's Jocelyn Bell's little green men. And she wrote, it was highly likely there would be 2 lots of little green men on opposite sides of the universe. Both decided to signal at the same time to a rather inconspicuous star on a rather curious frequency. So at this point, one knew that these are in fact real things, not just an artifact of electronics. They have electronics in '68. Well, this is a summary of some of these things on neutron stars. They made their gravitational collapse of massive stars and supernova explosions, and also in binary neutron star mergers. The matter they contain is the densest in the universe, and up to the standard density measurement is what is called N0. N0 is if you take a heavy nucleus like uranium and look at the density in the middle of it, that's the sort of saturation density of nuclear matter. That is about 0.16 particles per cubic Fermi, which is 3 × 10⁻⁴ grams per cubic centimeter. It's very heavy. Compared to white dwarfs, it's infinite, much more heavier. The white dwarfs range in density 10 to the 5, 10 to the 9. And neutron stars have densities of well above 10 to the 14. What holds it up? In fact, an interesting question: what holds you up? Why aren't you? I mean, your atoms are pretty far apart. The atoms in your pants are far apart. The atoms in the seat are far apart. Why don't you fall through? Huh?
Degeneracy pressure.
The electron degeneracy pressure. Your pants electrons and the share electrons don't want to be in the same place at the same time. See, they said that's what supports you in your share. So the gravitation of basically the nucleon pressure is supporting the stars, and the higher density is the quark factor, as I'll describe. And since their first discovery is pulsars, they've been seen in quite a variety of systems: pulsars, binary X-ray sources, soft gamma repeaters, magnetars, very high magnetic field neutron stars, ultraluminous X-ray sources, fast radio bursts. These are sort of splurges of millisecond bursts of radio. And been quite a mystery, but I think they're being understood to come from magnetars. And of course, as I'll emphasize, you've been seeing binary neutron star mergers and also neutron star black hole mergers. And what's also interesting is there an astrophysical laboratory for studying cold, high density matter and quantum chromodynamics. Many years ago we built RIC. Which way is Long Island? Long Island, way out Long Island. This big circle of it at Brookhaven to study high density matter, but the trouble is one makes only hot matter, not cold matter. So this is really the only way just to get a handle on high density matter and keep cold matter in QCD. Let me just describe as we go further into the star. The outer crust is made of ordinary nuclei. What's interesting about these nuclei is as you go further in, they get more and more neutron rich. And you have to ask yourself, why are they called neutron stars? Because as we'll see, the matter becomes more and more neutron rich. And why does it become neutron rich? Because the solids have Fermi seas of electrons. As they get denser, the Fermi energy gets higher and higher. What happens is it begins to pay for an electron to be captured out of a proton to make a neutron and a neutrino. The neutrino would simply leave the star. So in the process of formation of the supernova, you want to get a lot of beta electron capture processes. And so you convert protons into neutrons. Now you ask, how come it doesn't go the other way? Why don't these neutrons simply beta decay into proton, electron, antineutrino? And the answer is the electron states is the Pauli principle, so that the electron states are occupied up to a certain level of Fermi energy. And so that means that neutrons trying to decay will find, if their energy is too low, they cannot. The decay process is smaller. So as you move into the star, you see there's a Fermi sea of neutrons, a smaller Fermi sea of protons and electrons. The number of protons and the number of electrons have to equal this to preserve charge control. Neutrons have no charge, protons have plus charge, electrons have negative charge. And so as you move into the star, in the outer region, you start with iron 56. Iron 56 is the ultimate ash from nuclear burning. Now you read in the books, it's nickel 62. But nickel 62 is the most tightly bound nucleus. But if you add in the electrons as well, then the best amount, the tightest bound system is iron 56. So this is the ultimate ash. If you burn things, they extract all the energy you can from matter. You'll be left with iron 56. So ideally, that's what you imagine sits in a neutron star on the outside. What really sits in a neutron star on the outside depends on the history of the star. Is it accreting matter from the outside? To what extent does that matter get burnt and so on? So the actual structure of the outside is much more complicated. As you go further in, you get nickel 62, then nickel 64. Then the next you should jump to selenium 84, germanium 82, iron 76. I mean, these are all imaginary nuclei in the laboratory. And then further in, you get a range of molybdenum 124 all the way through strontium 120. And just to remind you, strontium 90 was the milk additive, the thing that got added to milk from nuclear fallout. And so this has a lot more neutrons, krypton 118. The characteristic of these nuclei is all this group they have 50 neutrons. These are all nuclei 50 neutrons, which is a magic shell, closed shell number. In the next region, you go to 82 neutrons, also magic. Now this is lovely. Is it true? We don't know. The problem is that why are 50 and 82 magic numbers for nuclei? This one induces for nuclei that sort of roughly equal numbers of neutrons and protons, and the actual magic numbers depend very much on the spin orbit forces between the neutrons, the spin orbit forces between the nucleons here, and they can be very different for nucleon-rich nuclei. And so the question is, do 50 and 82 remain magic numbers? And there's a big experimental program going on to understand this here. I don't have an answer, but it appears to be no. That rare isotope accelerators, they used to be called radioactive beam accelerators. We're not allowed to say that. So there are RIKEN in Tokyo, rare ion beam facility. I mean, this RIKEN is common. RIBF, which is the facility being built in Michigan State. GSI in Darmstadt is building something. I'm backwards. This is RIKEN is RIBF, and Michigan State is FRIP. There are a limited number of names you can have. They're all awful names. Really. The Korea, this used to be called the Korean radioactive rare ion accelerator, which in Korea, which is a very nice name, but it's Korea. But it got changed to rayon. But anyway, but
But
the
this
answer
is just theoretical,
Huh?
that's what's out there, is that correct?
what is
In regions 2 and 3, that's the theory of what should be there, or is there a way
that's
to?
the theory of what should be there.
But there's no way,
Well, we have to learn how the shell structure gets modified.
I meant to say there's not direct up. How would you know if that was right, observation?
Oh, because people doing experiments and discovering, for example, closed shells of calcium.
No, but I meant about neutron stars, are they actually like that? How would we know if you're right? if they exist, supposing those nuclei exist,
Does it make a difference?
no, okay.
I don't know. I honestly don't know the answer to that. But however, what makes a difference is the thickness of the crust. Your question?
Well, I guess, yeah, are there experimental methods to determine the chemical composition of the neutron star crust? Or is it all just?
Say again?
Are there any experiments you can do to determine the chemical composition of the crust
Not, well,
or observations, I guess?
you know, there are observations that look at thermal history in the crust. And so you get to measure, for example, the thermal conductivity of the crust. Okay. So now as we continue in density, one gets to the stage where you're making more and more neutrons. And you just think of the neutron nucleus as simply a square wall potential. You begin to fill all the bound states that the neutrons can occupy. So you make the next neutron electron capture. Where does it go? It has to go into continuum state. And so this is the process that occurs at around 4 × 10⁻¹⁰ grams per cubic centimeter called neutron drip. And so that's in this region over here. And so what you have is a sea of neutrons, just like you have a sea of electrons, free neutrons running around. And in addition, you have nuclei. But you ask, what about the protons? The protons don't appear to drift. Protons appear to want to stay together. This is all based on that calculation. And so the protons stay together until the nuclei merge together to form the liquid interior, but there's a sea of neutrons. One interesting thing about these neutrons over here is they're superfluid. In fact, this outer region of the neutron star here has more grams of superfluidity than all the other superfluids. So certainly all the superfluid laboratories on Earth is a major source of superfluids. And it's a very high temperature superfluid as well. I mean, with critical temperatures on the order of 10 to the 10th Kelvin, which is cute but useless. This one, this is a very nice, all the lovely calculations of nuclei. So we start with zirconium 90, and the upper curve, I can't be too short. This is the neutron distribution, the proton distribution. As you cool that, as the density increases, that's going down into the star. What you begin to see here at 1100 is this actually a neutron distribution doesn't stop, it continues out indefinitely. This is the beginning of neutron trip. So here more neutron. And eventually what you see is, this is again germanium at the time, germanium 32 protons, 982 neutrons, is the protons are down here, but and the neutron distribution eventually just becomes sort of sinusoidal. Eventually what happens is, well, I'm about to tell you this wrong, but eventually what happens is this thing just smooths out completely. But it does something much more beautiful before that. There's this funny regime called posited nuclei. Now, if you remember, in the old Bohr-Wheeler criteria for nuclear fission, if you have enough charge in a system, the system will want to pull apart. The Coulomb charges, the protons don't want to stay together. The system will be formed. Well, the same thing happens here. And what you find is that this has these wonderful food names. You start with ordinary nuclei here, but then they want to start deforming. They form long rods called spaghetti, and eventually these rods turn to sheets, lasagna, and then you continue around here, and so these get thick, and to the inside they get sort of anti-lasagna rods in space. The pre-neutrons form the rods here, and finally turn to some balls. Is the cheese here. This is great fun, lovely pictures, lovely jokes, but it's actually very useful, very important, because it turns out that this is in the high density region. Over half of the mass of the crust is in these funny configurations over here. It's not something one can ignore. For example, if you want to calculate the thermal conductivity of the crust, so the cooling of a neutron star, you have to worry how do electrons get through such structures over here? How do these structures emit neutrinos? The neutrinos actually have a rather complicated band structure. And so a lot of subtle, interesting physics that can make a difference here. Now we get to the deep interior.
Aren't you gonna tell how thick the crust is?
Am I going to tell how thick the crust is? No,
You're waiting to, you're saving that.
it's a secret. They're kilometers, roughly kilometers. But the actual thickness depends on model calculation. Depends on the total mass of the star. But the larger the mass, the thinner will be the crust, because gravity is much stronger.
That guy in NASA was talking about something that was a centimeter, another piece of it that was a meter, and so on. So there are all these little structures.
Okay, and so the interior is primarily begins with neutrons, protons, and electrons. The immediate question you can ask: can these things be superfluid or superconducting? Neutrons, yes. Protons are probably 5% protons, 95% neutrons. But the electrons are normal because you calculate the transition temperature, and it's roughly 1/137th electromagnetic fine structure constant. And so the transition temperature is whatever scale Fermi temperature times e to the minus 137. That's a very small number. So the electrons are definitely very normal. People have debated over the years, possibly meson condensations, which are rather fun. Maybe droplets of quarks. I'm not going to talk about these at all. Oh, If it's for me.
Music, but I can't find them. Or maybe it's content.
the phase transition from the crust, where the positive nuclei turns into the uniform interior, is probably the density around 70% of nuclear matter density. But this number is still rather uncertain. And one needs good calculations of the positive nuclei as well as the liquid interior. And there are certain levels of uncertainty there. Well, how does one go about actually understanding the many body physics of the liquid interior? Well, there are several games one can play. One thing you can do is sort of good standard conventional physics, which is go out, you scatter nucleons together. And you scatter, there's really a complete set of data of up to 300 MeV, which is the pion threshold. If below 300 MeV collisions of nucleons, you don't get pions. So from that data, you could fit them with inventing nuclear forces, like the argon V18 two-body potential, and then you add in what you know about deuterons, what you know about helium-3, tritons, and you can make rather reasonable nuclear forces. So then you sit down to solve the Schrödinger equation. Now, in the old days, solving the Schrödinger equation was very hard, but with the advent of big computers, you can really do the many body physics really well. What you find, it doesn't work. What you see is, nuclei should have a binding energy, what's called nuclear matter density. This rows there, this is my N0. About 16 MeV binding energy. What you find from these calculations is you actually get roughly reasonable saturation binding energy, but the density is much higher. Something's wrong. What's wrong here is question 3 body forces. Forces that involve scattered nucleons interacting together through other states higher, like excited states of nucleon, delta resonance and such. And what you need here is you need to somehow push this red part of the curve up and pull it down here. And so the 3 body force is a funny game because you don't really have a very fundamental handle on it. So there's been a very popular recent approach called chiral effective field theory, which I'll say a micro word about. And also people do relativistic field theory models, which probably are less grounded experiment. But the important point is to understand what goes on in neutron stars above nuclear matter density. You really are making an extrapolation. You can't do measurements in that region here. So you need a theory that you can push up to higher density. And how well does that work? Well, that's a source of problems here. The chiral effective field theory is looking at just many body interactions of various kinds. I won't go into details of the diagrams here, But when you're doing really expansion in powers of the momentum scale, you're looking at in the interactions here. And so here's what we can conclude about energy per particle versus density. And down here looks pretty nice. Nuclear matter density is 0.16 here. There's some range of it. But once you get to twice nuclear matter density, the thing breaks down completely. There's too many uncertainties. And it's no longer very useful way to calculate. The whole batch of people associated with this game. I guess Steve Weinberg really started very early. Okay.
Question?
Well,
Can I ask you a question?
yes.
So
Yes, you
when
said.
one considers nuclear matter in loud NC, it turns out that it has a structure of a solid and not of a liquid.
Yeah.
That's very easy to show. Now the question is here, which is not cloud N, but NC equal to 3, but with very high densities, whether it's not also a solid structure rather
Yeah, I
than.
mean, there's something you might imagine. I mean, if you take a system like helium or hydrogen, or you condensed matter system, and squeeze them, they become solid. Well, I guess hydrogen is always solid at zero temperature. But the helium turns solid. And people have looked at this. I mean, really, the only calculations I know are within ones where you understand nuclear forces. You ask which is better, liquid or solid, and the solids fail. So there's no evidence of solids being better. But that's really it depends on the structure of the interactions themselves. Okay, so what do? You calculate away, you solve a theory, and then you proceed to construct what are called neutron star models. And so what you do is you calculate energy density, you calculate pressure, which is given by order of the thermodynamic derivative of the energy with respect to the baryon number, with density. And then you plug this in the TOV, Tolman-Volkoff equation, which is just the ordinary equation for hydrostatic balance. The only difference there are various terms among c squared downstairs. Those are general relativistic corrections. But otherwise, you recognize if you forget about the whatever c squared terms, this just thing tells you how the atmosphere falls off with increasing height. So you solve this, the mass, you integrate the density. This looks like the ordinary non-relativistic formula, but it's actually very subtle. That turns out this way. And so here is a calculation done on calculating about the argon potential done by my colleagues, Ari Akmal's student, Vijay Pandyapan and Jeff Ravenhall, both of whom passed away in 1998. And what you see here is this as function of density goes up, turns around, comes down. The best calculation, this is with a 3-body force called the Urbana-9, U for Urbana, and with some relativistic corrections here. And what you
So rotation doesn't matter here.
is it what?
Rotation does not seem to matter.
The rotation does not matter because they're relatively slow. There's some interesting stories in there, but that's a reasonable question. Ask me again when I talk about nicer data. And what you see is it goes up and it comes down. So here, this star has with nuclear forces. Here, this best theory is giving something like 2.2 solar masses from the max here. The corresponding radii over here. These are families of neutron stars. So what you see as you change the central density, it'll go up and then go down. And these stars out here are stable, they can't exist. And what you find the density here, if you're far out, it goes up like this and up, increases to around. The picture here gave something roughly in the order, something in the order of 10 kilometers. I mean, these are relatively small now. And so this is a typical way you calculate a model. I don't want to push this as the answer to anything, but it's just pedagogical purposes. But this is a pretty lousy approach altogether. I mean, you can ask the question. I said we're doing extrapolation from nuclear matter density to higher. This is fine in the region of nuclear matter density where we have a very good basis of experiments of ordinary nuclei. But one problem here, as you go up to high density, the sound speed, which you calculate as simple derivative, that begins to exceed the speed of light. And there are sort of philosophical problems with that. I mean, what's the saying when you go back in time, shoot your grandfather that you can't be born? If you go by the causality. That's not good. But then you might ask the question, what about 3, 4, 5 body forces? What about 3 body forces, 104, 105, and so on? The effective field theory tries to take this into account, parallel effective field theory, but it begins to break down. But does the whole thing make any sense? Can you really describe nucleons with forces between particles? These asymptotic particles here. And can you really even talk about neutrons and protons, these higher densities? The particles, we go to the stock room, you ask for a bag of neutrons or protons. Are those really the right degrees of freedom? I mean, a very trivial example, but analogy what you're doing here with nuclear scattering experiment. Imagine you had a complete set of scattering data for niobium atomic scattering, atom scattering here. So you write that niobium effective potentials and stuff. Would you, on the basis of that, predict that niobium metal was a superconductor? No, you can't. I mean, what's happening, new degrees of freedom become important. And so what's happening is the particles are really beginning to overlap, and quarks are going to begin to become important. And so it's like trying to describe. Suppose you had a complete hydrogen theory of the egg scattering at low density, at low velocity, the eggs don't crush. Could you predict from that what egg matter looks like at 10 times density of closely packed eggs? The answer is no, because it doesn't look like this anymore. It looks like that.
I find it a little surprising. It seems like all the eggshells went away.
What?
It seems like all the eggshells went away. You're missing.
Oh, yeah. Good.
There's no explanation for that.
But the eggshells go away.
The brown and white and not each other.
Okay. So I mean, the thing is, these nuclear models, they look like kind of nice, but the fact that something is nice does not make it right. And I always like to give this example here of the simple theory of 16 over 60 will cancel 60. It doesn't make it right. It works. 19 over 95. 18 over 85. It's possible. So the fundamental message, the fact that it looks good does not make it correct. Okay, so we're kind of stuck in a while. So let me just say a little bit about observational data. So one of the wonderful things that happened in the past number of years is observations of neutron stars have become very, very good. There's a wealth of information coming out. One thing is, one has found heavy neutron stars and pulsars over twice nuclear matter density. That tells you the equation of state must be very, very stiff. I'll mention this. Massive radii are being measured. First, there was from looking at X-ray binaries, one could get some information on mass massive radii. But there's a very beautiful experiment called NICER, which I'll explain in detail. I can measure massive radii much more directly. Since 2017, we see gravitational waves from neutron star mergers. I'll explain that. And that begins to give you a lot of information. There are things called glitches, the fact that the pulse repetition frequencies in pulsars can suddenly speed up. Pulsars can appear to speed up. I'm not going to talk about that. And there's another interesting window in neutron stars, which is the cooling of neutron stars as well, which I will mention. So here's the picture of what we sort of know about neutron star masses. There is the famous Hulse-Taylor pulsar, binary pulsar, which they got the Nobel Prize, for which the scientific secretary of he was giving a talk in Copenhagen on that. The scientific secretary of the Swedish Nobel Committee said, well, we made a mistake with Bell and Hewish, but here we were very careful, and we also awarded the prize to Joe Taylor. Taylor, I quote, was the advisor, also was a graduate student. He got it backwards. But but notice that these are all range about 1.35, 1.4 solar masses. And so everybody, 1.4 is a very famous number. 1.4 is the Chandrasekhar mass. And if you ask the question, what is the maximum mass of electrons degeneracy can support, the best collapse, that was calculated by Chandrasekhar, 30s. And that is the 1.4 solar mass is the maximum you can get. Has nothing to do with neutron stars. But everybody thinks, but because this number is almost 1.4 is significant, but it's not. Okay. And the various information on neutrons, various neutron star guesses, everything are error bars. But there have been three rather good measurements here of three neutron stars which I mentioned here. Interestingly, on this picture, if you look at this picture here, there's a question, what do we know about black holes? Black holes come down maybe a mass something around 5 solar masses here. And there appears to be sort of a gap here between this 2 to 5.
Gordon, maybe be sure to talk plenty loud because when you turn toward that, it may be hard to.
I can hear myself. Okay, thank you. So anyhow, these three objects over here. 1.928. Then there's the next one over 2.01, and then this one, the heaviest neutrons are 2.08. And that's very interesting. Because what it tells you, you immediately learn, if you learn a lot about the equation of state if you measure a heavy neutron star. And how does that work? If you make a graph of mass versus central density of the stars, if the equation of state is soft, you can't support very much mass when you go around the high central density. If the equation of state is stiff and hard to compress, you can't go to very high densities, but you go to much higher masses. So the game is if you see a neutron star of mass above a certain limit, any equation of state, like this over here, cannot be correct because it cannot explain that star. So immediately, the higher mass you measure, the stiffer must be the equation of state. So you throw out all these other families over here. So what we learn is that the equation of state is fairly stiff. It's not as stiff as the equation of state from pure nuclear matter, but there's interesting data on that. If you just simply concentrate on binary neutron stars, mass around 0.4, then that's consistent with the soft equation of state, but the heavy ones are not. Heavy ones show the equation of state must be stiff, hard to compress. Now let me turn to NICE. NICE is a wonderful thing. This is a sort of refrigerator-sized experiment that was flown to the International Space Station in June 17. Summer of 17 was rather remarkable. 17 there was the wonderful eclipse. It flew nicer here, and the other thing was the discovery of the binary neutron star. All in the summer. And it does very good X-ray timing. The spectroscopy from 0.1 to 12 keV. And the promise is it can measure neutron star mass and radii to order 5%. That is still a work in progress. What was wonderful is that in April of this year, NICE announced results for the heaviest neutron star. At a press conference, they announced a radius measurement for this 2.08 solar mass neutron star. How does NICE work? I mean, this is really, really brilliant. You know that light is bent by gravitational mass, and light bent by the sun, which dates back to Einstein's law of relativity, confirmed in 1919 by Eddington and others during the eclipse. And so, if light goes past it, the observer's not here. If light goes past a neutron star, it will be bent here. So you can sort of begin to see behind the star. In particular, if there's a hot spot on the star, you can see that hot spot, even though it's gone behind the star, just because of relativistic bending. And here's a lovely movie. What you see here this is no gravity. And so, so the spot comes into visible eclipse for half the period, and so it goes up and down. However, due to general relativity, you light bending, or you see behind the star, and so what you see is you can actually begin to see the spot over the entire period over here. So what Neisser is looking at really is how much in a rotation period you actually see behind the star. Now, of course, the angle of bending is dimensionless. So what it's measuring is really the ratio of relativistic units of the ratio of the mass to the radius of the star, so what's called compactness. However, there's much more information as well by looking at further general relativistic corrections, and you really get quite independent information on the mass and the radius.
Should I expect that the areas under those two curves should be the same?
Say again?
Is it just because of the sketch that the areas under those curves don't appear to be the same?
I don't see the question.
It looks like the total amount of light emitted is more on the right than is on the left.
Oh,
The amount of light we see is big.
yeah,
Right, so
It's
what-
sort of its lens.
Right, but I mean,
yeah,
is it
you're
because-
asking why this guy's higher over here and lower. I don't know the answer.
no, I guess what I'm asking is like, it can't be isotropically true that you get more brightness everywhere, right? So it must be dimmer somewhere if it's brighter towards us. I'm wondering what says that direction.
It's reasonable, yes, but just conservation of emission.
Right.
Good. Okay. Okay, so so here's the data that was announced. Cole Miller at the University of Maryland with Fred Lamb in Urbana, they measured, and what they did is they looked just at the nicer data for this one star, which is this 2.08 solar masses. Measured very recently the Canadian hydrogen something. And then it's a radio pulsar, and they really see massive 2.08 plus or minus. And they conclude, just from looking at the NICER data itself, plus a measure of the background from the European satellite, the X-ray satellite XMM, which you can look at sources but no timing resolution, measure X-ray background. They conclude that the star must be between 13.7 plus or minus kilometers, and the mass of 2.062. However, that's a little unfair, because what you know a lot more about nuclear matter and neutron stars as well. Not just from our data, you know the fact that there exist heavy pulsars. You know something about nuclear physics, some ideas of energy versus density of particles in nuclei. When you put that information in, this number drops to about 12.3 plus or minus 12.7 kilometers. But this is the one signal level here, which is 63% confidence in the other one. There's another independent group in Amsterdam that conclude roughly the same thing. I don't want to get into the experimental, into the details here. Okay, now, so that's what we learned from Neisser, and I'll come back, you'll see more of this. A very important thing has been gravitational radiation, which is really providing a real new window on the universe altogether. And in in August 17, 2017, there's a spectacular event of two neutron stars merging into each other. And this is really one of the most spectacular discoveries I think ever. It took place in the Hydra constellation at the South Pole, when they just what the masses were of this object here, two neutron stars with masses within the range 1.36, 1.6, 1.7, 1.36. These numbers are the same. For a very obvious reason, which is you pull one of the higher mass and the lower mass. And the radii is something about 11.9 plus minus 1.7. And this is a picture of the two neutron stars. This fuzz that you see over here, that's actually gravitational radiation. This is not a photograph, this is a master simulation, of course. Boom. And then this what's called a kilonova is produced, and which various components. And what you know about the kilonova, is various heavy elements are produced in it. And this may be one of the great mysteries is how do you make the heavy elements, materials like platinum, silver, gold, and such? Because this has to be neutron capture on nuclei. Well, where do you get the neutrons from? Well, neutron stars are fantastic because neutrons are these big balls of neutrons. As they merge together, all these neutrons are released, and there's tremendous amounts of neutrons to capture. The details are still being worked out here. This is the picture. Yes.
There it was.
So what you hear is whoop, ding. The ding was the gamma rays measured by the Fermi telescope in complete independent measurement. The initial one here was this is measured by gravitational radiation, LIGO. Ding. She showed me, it was a beautiful chart. But what's interesting about this one, however, is that actually Fermi discovered this first. Even though their signal was 2 seconds later, they told LIGO, go back and look at your data. And because the data was there, LIGO analyzed it.
Well, Fermi discovered it, but they didn't tell LIGO to look for it because it was, right?
I
It
thought they
was,
did.
I think it was below their threshold of, well, we can discuss it. Maybe I'm mistaken.
Okay. Oh, it's nice, okay. But since then, there have been a number of other interesting events discovered by LIGO. Hence, the binary neutron star that was measured in April 25th, 2019. I was going to say last year, but it wasn't. Unfortunately, LIGO, there are two detectors of LIGO. There's Livingston in Louisiana and Hanford in state of Washington. Unfortunately, only Livingston was on, so it didn't have any real ability to triangulate. And so there's no localization of the sky. This is the Hydra constellation, and what could really pin it down from the gravitational data that had to be associated with this brightening object. This is the neutron star merger actually photographed in Hydra. There have been other events, a black hole merge of 23 solar masses with some of these 2.5, 2.67 solar masses. These merged together. We don't know the answer to the question. Is this thing here a neutron star or must it be a black hole? I mean, after all these years, all this study, we still don't have an answer. What is the maximum mass neutron star we can have? There's a belief it must be around 2.3 solar masses, but it could be larger. I mean, I'm certain not that my house on the 2.3 number. Okay. Another event actually took place the next day here. 5.7 merging with 1.5 solar mass object. Is probably a black hole neutron star. Again, there's no electromagnetic signal whatsoever. Only the very first one here had this beautiful electromagnetic signal. But if you the next generation detectors, which should be on air by 2030, should be seeing events on the order of perhaps 100 years or so. Why so? Huh? That's very strange. Okay. This is just a very beautiful map called Mass in the Stellar Graveyard. And what you see if you look carefully over here, you see objects. You can't see these lines over here. This object is associated with these two objects associated together. And these show the objects that merge together. And unfortunately, the system is not good enough to see the detail here. But this is showing the 1914. If this object was so much lower, the 1708, 17, and so on. And so there's something like on the order of 8 compact objects have been discovered gravitationally here. To what extent these are neutron stars or are they black holes is completely uncertain. In fact, when LIGO announced they measured a neutron star versus a black hole, they just have a mass cut. They're not doing any physics that tells you whether it is a neutron star or not. If it's heavy, it's called a black hole. If it's light, it's called a neutron star. And it's only if you see an electromagnetic signal, it can be the information as to whether whether it does involve neutron stars. Okay.
Well, the binary neutron star merger, the pure gravitational wave signal is very different from a black hole merger. No? Oh, you're saying for the same mass. Maybe
The
that's-
same mass, yeah. Jenna, this is sort of a picture this is the periodic table, roughly, this is more a cartoon, but these elements in purple are claimed to be made in binary neutron star mergers here. And so it could be what is making all the gold in the universe this way. And so next time you look at any gold, like Paul's making over here, think of the fact all those atoms came from binary neutron star mergers. Amazing. Not a gold mine in South Africa, but binary neutron star mergers. The only nucleus of which we really has any spectroscopic evidence has been strontium. That was there's some uncertainty to how well this works. Okay, now what I want to discuss in the next 2 hours. Matter, what goes on with equation state and such. And here's a phase diagram I wrote down of what matter looks like at various densities. This is those of you who do low energy physics. Everything you do lives in this pixel around here. This is nuclear matter here, all the way up. And what you see here is that if you go very high temperatures, 200 MeV, densities 510 nuclear matter densities, there's a phase transition here. Where out here you have deconfined quarks and gluons, and in this region you have hadronic matter. Hadronic matter means familiar things like neutrons, protons, ions, and such. Out here you have quarks. And so many years ago we built the relativistic heavy ion collider to begin to study these things, but unfortunately we only get information up here, we don't get information down here. And so what happens in heavy ion collisions? Two nuclei collide, they pass through each other basically. They begin to fill in space with excited states in the vacuum, pair production. This is the quark-gluon plasma here. This is well, what's interesting here is that people like quarks every place but neutron stars. You discuss the early universe, you have quark matter. Heavy ion collision, you have quark matter. Future electron ion collider will certainly be discussing the nature of quarks and gluons inside nucleons. Somehow neutron stars, people, there's a strong feeling, well, it's only neutrons and protons. And people, there's some reluctance of people who want to take quark matter seriously, but I think one has to. But one problem is it's very hard to calculate because it's QCD, quantum chromodynamics. It's highly nonlinear theory. And we say, well, you do a lattice gauge theory to calculate. The trouble is you can't do lattice gauge theory at finite baryon density due to a mathematical mystery called the Fermi sign problem. And you end up, instead of having a positive measure, you end up with a complex measure. That's a nuisance. Okay. This just appeared last week. While Leo was trying to recreate the conditions that occur seconds after the Big Bang. Turns out they're extremely not pleasant. So we're trying to recreate the conditions that occur on the tropical beach, early 2014. Okay, so this is the phase diagram. There's some interesting last gauge theory calculations. Which you can't do it. But going up the temperature axis, you can do it. This is zero density vacuum. What you find is that instead of this nice division here between hadrons and quarks, there's a crossover over here. And that seemed to be pretty good. And then that's rather problematic. Because what it says is that the matter here is continuous with the matter of here. Here we can have the quarks and gluons running all around freely. Here we can't. But if it's continuous, we have quarks and gluons running around here. We can have quarks and gluons running around here. So can you have quarks running around the room? How many high energy people think yes? Anybody think the answer is no, you can't do it. And what it tells you is that this naive picture of confinement you can't have free quarks here, you can't have free quarks running around here. What you can have within the given region of space, you can have quarks running over a large area. So for that in a heavy ion collision, I showed these two things going together with the side state the vacuum. In that limited region of space, one can have quarks running out freely, but it's not. It can't be over very large distances. Don't ask me about the early universe. That's complicated. Okay. And so that's sort of interesting. In fact, what it's telling you, in fact, is that if you look at the phase diagram of matter, hadronically plasma, this is really just a liquid gas phase transition. One can go from hadronic state all the way continuously to quark-gluon plasma state. Exactly as you do in water. Water, this is pressure versus temperature at 374 degrees Celsius. There's a critical point, and you can go from water vapor around to liquid water continuously. And you can do the same thing in phase diagram. Strange. The thing that distinguishes phase diagram is that at low temperature, so this critical point may not exist. People sort of loved it for historical reasons, but it may not exist at all. This may be continuous structure. There's a change in the symmetry energy down here, the symmetry, because here one has pairing of quarks, and so you break the U1 symmetries here, which you don't at high temperature. So this state, the upper state is different from lower symmetry of the lower state here. So let me so heavy ion collisions, there's a big program of heavy ion collisions to look for this critical point over here, which so far has been unsuccessful, and it may continue to be unsuccessful because there may not be a critical point, because there's no reason to have one. The electron ion collider, however, should be able to begin to explore what's going on down here. So stay tuned on that. Now, okay. Now I just want to just very say, how do we go beyond what we have? How do we begin to what works? The standard method of calculus, how much time?
When did we start?
Pretty close to time, maybe
Huh?
4:02 or something.
Let's say,
You
How much-
started about an hour and 4 minutes ago, I think.
okay.
Well, Paul started, then he gave you such
When
a
you
long
leave,
introduction.
just-
Yeah, so we started 5 minutes.
We'll leave for dinner or something.
How much longer you got?
Maybe 10 minutes.
Okay.
I can go to 56 megabytes. Wow. We spoke fast in Brooklyn. Very fast.
Keep it down.
Okay. Yeah. Okay. There's always a question of how do you calculate quark matter cores of neutron stars? Now, I wrote a paper a long time ago, which actually wrong, which set the field back quite a bit. Which is, you observe what you think you do is you write down energy per particle versus density. You write down a hadronic phase over here. You write down a quark phase, and then you observe that, well, the quark phase has lower energy than the hadronic phase at high density, therefore it's the right one. And what you do is, if you know thermodynamics, you make a Maxwell construction between the two, and you find you go from here to here discontinuously. And so what you find, well, this upper point over here, typically about 10 times nuclear matter density, way too high to be interesting. And so maybe you have tiny little quark cores in neutron stars. That was the conclusion of this. But as I said, it's wrong. Because there are two assumptions that are really very bad, which we didn't understand at the time. Assumption one is, by the way, the zoom here cuts off the bottom. So there are more words down here.
is what's happening is that, yeah, it's
I know.
obscuring it.
I don't know. But anyhow, the two bad assumptions. One is you're assuming here that high density of two competing phases, a hadronic phase and a liquid phase, and go back and think about eggs. You can ask the question, which is preferred high density? Eggs and shells or a liquid egg? The nucleons don't make sense because they're high density, they're completely overlapping. They cannot be the right degrees of freedom. So the assumption here that you have two separate phases, but must be wrong. The other thing, even if that were true, is this Maxwell construction automatically picks out the softer phase here. So that means even if you could have quark matter, it has to be soft in order to qualify as a possible state. If it is soft, it means you can never, it can't support big neutron stars. And so there's no way you support a 2.808 solar mass neutron star on the basis of quark matter, if this picture's right. This is a wrong way to do things. So we started doing that. And so the simple picture we have, this is a few cartoons, is if you look at pressure, chemical potential, this is the nicest variables for doing thermodynamics. We know what's going in the nuclear regime down here. Here, though we can't model QCD exactly, there are models like Nabu Jabalacino, we put some idea what's going on. And but the thing is, what you would say, well, you could do an extrapolation between here, but it's really highly constrained. You're not allowed to have inflection points because the second derivative is just the compressibility. That has to be positive. So it can't go like this. It has to go smoothly. And so we did some modeling with the various typical interactions, but two important points here. The two important features of the interaction we took are a vector repulsion between the quarks, just like a hard sphere in heavy ion collisions. I mean, in cold atoms. GV is a positive number in this Lagrange, it's a minus sign, but GV is just telling you the repulsive interaction. And H, this is a very, very fancy we worked out. They're just involve BCS pairing. So this H is really the parameter that's governing BCS pairing. And so while we write down things, just grab the two parameters. And so the picture is very simple. The minimal model, you take free quarks, and this goes up here. You discover that this is far too soft to support neutron stars. You need to do something else. So next thing you say, well, let's put in some stiffening. You put in stiffening, this goes all the way over to here. This is the repulsive interaction. This, you can't join this to this unless you have an inflection point in between. That's unphysical. So that's the unphysical inflection point. And of course, Mr. Simpson tells us we can't do that. And so we have to, what seems to be interesting is we put a word up for pairing. And pairing shifts this curve over to here, and then you can in fact construct a consistent picture over here of the pairing. And this is about a large amount of pairing. And that's wonderful. There's one thing you know, that if you started with quark matter, you go down in density, you want to turn into nucleons. The quarks like to pair, of of course, nucleons are triplet pair, three things paired together. How does that happen? Does it happen by forming diquarks, two quarks, and the third one comes on? That's unknown. But certainly, the short range correlations want to encourage quarks to be together. And so the fact that this is a much larger number than you expect is actually a very nice outcome. Okay, and so I'm just going to show you some results. But so this is an equation state. LIGO people, LIGO people, on the basis of the 1708-17 binary neutron merger, had this lovely picture over here, and our equations of state from 2 years ago sort of went rather nicely through what they did over here. That was cool. But then, of course, came the next actor in the room, which was the nicer measurements. The nicer is coming out with somewhat larger mass. And what they were finding, I was just superimposing on a picture, the nicer equations of state, and they seem to be swooping up much more between these registers. There's some degree of stiffening there. And so we have to ask the question, can we improve on that? And the answer is yes, we can, in various ways. I won't take the details, how we do it, but we can see, begin to get, this is pressure versus density, get such an increased stiffening over here, which looks rather nice compared to old time. And finally, these are masses versus radii, and so we can really extend things out here to get things on the order of 12 kilometers. And that's within, certainly within the one sigma error bars over here. What NICER finds, however, is that their best equations give a curve that's almost vertical. It's not clear, and we spent a workshop at Aspen with Paul Mills and data analyst. To what extent this you really should believe it? Well, how much of your work to if this looks vertical? The answer is not necessarily. So this is the best I can do. Mass versus radius, and it appears to be sort of around 12 kilometers. But there are these error bars. This is the 95% confidence out here. These things are moderately consistent. There may be more work to be done. So finally, this is yet another calculation. You don't want to hear about speed of sound, but one interesting result, an interesting analysis, is that the equation of state is there's probably no very sharp phase transition. This is showing a squishy equation of state. I would give you a region over here, mass versus radius. Very stiff equation of state look like this over here. And what really appears to be roughly in this region over here. So the possibility of having a squishy equation of state with the phase transition appears to be ruled out by the NICER analysis, which is very nice. So I think I'll stop here and just summarize where we go from here. These are great slides. But, where do we stand? The problem is by no means solved. One has to really understand a consistent phenomenological picture describing matter above nuclear matter density. We don't have fundamental theoretical handles, very good ones. But we'll certainly get much more gravitational radiation data over the coming years. And also NICER has a few more stars that they're analyzing as well. So more information there. So we really need to understand how quark degrees of freedom come into play. I mean, if you do everything about sodium gas, how when you squeeze it down to make sodium metal, how do you describe the transition, the onset of electronic degrees of freedom and such? And really, such pictures there for QC. Okay. And as I said, there's a huge industry of people just draw curves that fit the data. But that's not good enough. I mean, any automaton can draw curves. One really needs to understand the physics behind this at a microscopic level. And more questions, we don't know the boundary between neutron stars and black holes at all. These 8 compact objects, masses of the stellar graveyard plot, but we don't really know which of these are definitely neutron stars, definitely black holes. And finally, there's a lot more bread and butter physics to be done on this transport, cooling of neutron stars, how well the heat is transported from center out, heat is transported across. These are all challenges for the future. So the story is not finished, but I think certainly the past 5 years, have been tremendously exciting. I think I'll stop at this stage. Thank you. Oh, you got a call for questions.
Well, Glennis is the official host.
Oh, she is, okay.
Yeah. Questions about it. And we also could ask the online people.
Oh, yeah.
The absence of a phase transition,
It could be weak.
it could be weak, but it doesn't have anything to do with the property of gauge theories with scalars in the fundamental, or even there is no
Maybe it
phase
does.
transition.
Yeah,
Confined.
Particle. if I say SU3, that's scary.
You know, I am.
Okay. If you take so a symmetric SU3 matter of hadrons, it goes, and you look at the quark mount, there's no change of symmetry on root. It could be that you have complete continuous transition. That's called quark. Sorry about Frank Wilczek, Schaefer, quark-hadron continuity. It could, symmetry conditions don't tell you that you must have a phase transition. It could be very good. Or it could be minor with a phase transition. I'd be very surprised if it was big. Sure.
I don't understand, of course, your subject very well, but
I doubt that's true.
what I have a question. Speaking about this equation of state and pairing of quarks, I was thinking what could be possible other experimental signatures of equation of state, and I'm thinking about sound waves in this method. Sound wave.
Sound, yes. Oh, yeah.
Is it possible to observe some sound waves in the star? Somehow that might be a problem of equation of state.
A certain amount is understood, not sound waves. I mean, the sound speed is given the derivative of the pressure with respect to
that's
the
what I
energy
was
density. And what you know is that because neutron stars don't have very big radii, 12 kilometers is not terribly big. The matter is, low density is soft. I mean, the crust doesn't want to stick way out. It comes in. On the other hand, you have very high masses, 2.08. And so the equation of state has to turn from soft to stiff. What it tells you the sound velocities is that you go down here with a low sound velocity, but then and out here you should go to about 1/3, which is there's no scale of the problem. It's sound velocity squared is 1/3, but that's be a bump in between.
As a function of what?
Oh, I'm sorry, this is density, baryon density, but
Okay.
density going here, sound speed squared. So just general consideration tells you there must be something like a bump. So we calculated a way on this, and we find something looking like this. This is all right. And there was a recent paper on Archon that really shows estimates possible sound speeds. And it has this band over here where it can get larger, and then this are results superimposed. So it's nicely consistent. This is using nicer plus gravitation.
Is it possible to observe any of these?
To observe,
Yeah.
Well, I don't know how to answer it because first I would think, of course, is how much transport what can sound waves transport? That's probably not the principal method of transporting heat. But I'm sorry. There's a whole other class of measurements one can do, which is looking at the normal modes of neutron stars, R modes and such. And people do work on this. I'm not an expert.
How about from damping a binary?
Huh?
How about from damping a binary? Would the sound waves also damp a binary?
Yeah, but the trouble is it's hard to measure. I mean, the principal effect of binaries is gravitational radiation. And even Hulse and Taylor, they got the Nobel Prize, not for discovering this thing, but for noticing that the system is speeding up, completely consistent with the system emitting gravitational radiation as prescribed by Einstein. The quantum for a moment triples on squared.
As I remember in Aspen, there was a talk about that, and the trouble is at the moment as you get close to it's at the very final moments of the merger that you start to be sensitive to that internal structure. When they're too far away, it doesn't excite those modes.
Yeah.
And right now, the sensitivity and frequency isn't adequate to follow them.
I mean,
But
you could look at things up to roughly 500 hertz. the neutrons are not quite touching yet. And the millisecond calculus is the time scale. So the neutrons are still going around you. When they begin to merge, you really need to go to higher frequency. And future gravitational wave detectors and LIGO is pushing it. It senses to be higher frequencies as well.
In the
So
future,
the
it sounds
fastest
like
you
they
see
might.
that is 500.
Huh?
So the fastest you see this is 500 hertz.
Basically. Like that. Yeah. If you had a good ear, you could probably hear from the sound.
In your picture of the neutron star, is there anything about, is there an atmosphere that is transparent or not?
Ah,
towards,
that's a very good question. I mean, in fact, the question is, everybody should have asked, what about where these hotspots come from? If you have a star of the scale height of the atmosphere is infinitesimal, it's millimeters. In fact, that's where these millimeter-sized mountains. That's a simple solid state problem. And if you try to make a pile of strong gravitational field, you just pull it out. It's a strength of materials problem. But and so ordinary, there's no, we don't have 7 kilometers of gas in the ground neutron star. However, they have magnetic fields and they're rotating. And you rotate a dipole magnetic field, you get a very long, you get electric potential. And so if you rotate the typical neutron star with a 10 to 12 gas field, typical field, you get potential difference between the pole and equator of maybe 10 to the 18 volts. 10 to the 18 is a big number. And so there's a lot of electromagnetic fields which are carrying matter off the surface, making electron positron pairs with all kinds of things. And so there are magnetospheres that are fully charged particles. And you know this because you see pulsars. And pulsars are like wonderful radio stations that emit a signal at every frequency whatsoever. It's a magic radio. I mean, if you turn the dial on your radio, it's analogous to listening to music, and no matter what station you turn to, everything in between, you hear exactly the same music. I have no idea how this works. And so what the hotspots you see are particles that there's along the field line, matter is pulled up, it comes crashing back down, crashing back down, there's a lot of energy deposited as well. So you don't expect uniform temperatures either.
Sorry, you just mentioned this magnetic field that's outside the neutron stars, right? And you were talking about how you can think of it as just like this rotating dipole. But if we have these,
No,
I don't know,
the
could you-
rotating dipole is zero.
I mean, that's, yeah, sure. But if we can can we not look at the deviations that this has from some kind of a rigid body or something and use that to probe what's happening under the crust?
Oh,
right?
no, that's a very, very nice question. And the magnetic field appear to be very rigid. And what you would see when you look at the pulsars, if whatever was produced in the pulsars was sort of sloppily, the magnetic field was sloppily attached to the star, you would see great variation in pulsar frequencies. But the pulsars are up there with the best atomic clocks in time vectors. And they slow down as the stars lose energy, but the fluctuations are very minimal.
So if we consider the existence of new physics without like dark matter emission, so will it be possible that this kind of new physics change the equation of state of the neutron star? Or can we use the?
Oh, yeah, there's an interesting set of bounds, which I was also involved in these.
Yeah,
couple
or can
years
we
ago.
just use this to constrain?
Which, I mean, for example, there was a proposal of a dark matter particle. And then there was the mystery of the neutron lifetime. There are two ways of measuring neutron lifetime. They don't agree with each other. And so, well, the proposal was a solution where you have a dark matter baryon, so like of a mass roughly the same as a neutron. And what I quickly realized is if you have that if neutrons get turned to this thing, the pressure drops. It's like having a Fermi sea where you have more spin degrees of freedom. And so the Fermi seas are less energetic. The pressure drops and you can't support heavy neutron stars. So there is an industry of people trying to make interesting dark matter scenarios of neutron stars. And a whole other industry of people shooting them down. But it remains a very interesting question. I mean, it's another nice use of neutron stars to be able to test theories of dark matter.
Why is alpha G to the 2/3? Yes.
Where does that come from?
Why does
Ah.
it have to do with neutron star number of variables?
I won't give you an article, I won't give you an immediate argument. But if you, there's a very nice review article that I wrote, with some other people, reports on progress in physics. That has the argument. in the appendix.
I see.
I know,
So I will look.
Maybe we should thank you at this point.
Okay.
We can keep talking.